I see this as the title of the quiz, highlighting the core concept. How the perplexity parameter impacts the results of the T-distributed stochastic neighbor embedding, TSNE, algorithm. A technique used to visualize high-dimensional data. This is the central question I'll be answering in the quiz. I need to understand how the perplexity parameter influences the way TSNE displays high-dimensional data in a 2D space. This term refers to the entire sequence of steps involved in using TSNE. I will be focusing on one crucial parameter during the process, which is the perplexity. This is the type of data TSNE is designed to handle. It's data with many features which is difficult to visualize directly. TSNE helps me make sense of this high-dimensional data by reducing the dimension to a more visual-friendly dimension. This statement is incorrect. I understand that the ideal perplexity isn't fixed. It changes depending on the dataset. I need to experiment with different values to find the best one for each specific situation. Lower perplexity means I'm looking at smaller, localized neighborhoods of data points. This usually results in tighter clusters. However, whether these clusters are distinctly separate depends on the data itself. Sometimes clusters are close. Perplexity directly affects how many neighboring data points I'm considering. It doesn't control the exact number, but it influences the approximate range. A higher perplexity considers more neighbors and a lower perplexity considers fewer neighbors. With higher perplexity, I'm taking a broader view, looking at larger neighborhoods of data points. This tends to give me a better overview of the big picture relationships between the clusters of points. This is the ultimate goal of TSNE. I want to transform my complex, high-dimensional data into an easily understandable two-dimensional plot which I can visually examine to see the relationships between data points. I see higher perplexity as using a wider net to find similar data points. Think of it like this: you're casting a wider net to find friends. You'll find more distant friends, giving you a bigger picture of your social network. That's how higher perplexity gives you a more global view of your data. It captures large-scale relationships between data points. This results in a visualization that shows the big picture, connecting larger clusters or groups. Pretty cool, huh? Now, imagine you only want to find your closest friends, your inner circle. You're using a very small net. That's lower perplexity. It focuses on nearby data points, creating tightly packed clusters in your visualization. You'll see distinct groups, but you might miss the broader connections between these groups. It emphasizes local structure rather than global structure. The whole point of TSNE is to reduce the dimensionality of the data. Your high-dimensional data, maybe with hundreds or thousands of features, is simplified into a 2- or 3-dimensional space. You can then visualize the points, looking for clusters and patterns. Perplexity influences how those data points are clustered together to create that 2D or 3D representation. This way, you can better understand the relationships in a more visually manageable manner. I'll explain the impact of the perplexity parameter in T-distributed stochastic neighbor embedding, TSNE, a technique used to visualize high-dimensional data in lower dimensions. Think of perplexity as a knob that controls how TSNE balances local versus global structure in its visualizations. This question is asking you to understand the role of perplexity in shaping the output of the TSNE algorithm. It's all about how you want your data points to cluster and spread out on the plot. With a higher perplexity, I'm telling TSNE to consider more distant neighbors. This helps it reveal larger patterns in the data, giving you a clearer sense of the overall structure. Imagine zooming out on a map. You see the big picture, the relationships between cities, not just individual buildings. The lower perplexity setting tells TSNE to focus on closer neighbors. This makes clusters appear more tightly packed and distinct. It's like zooming in on that map. You see individual buildings, street details, but lose sight of the whole city's layout. I interpret perplexity as directly influencing the number of neighbors considered during similarity calculations. It's not a precise control, but it determines the range of neighbors involved. Think of it as setting the radius around each data point for determining its neighbors. This statement is incorrect. The ideal perplexity isn't a magic number, it depends entirely on the dataset. You'll need to experiment and find the best setting for your specific data. There's no one-size-fits-all solution. I see the perplexity parameter as a control knob in TSNE. It directly influences how many neighboring data points we consider when calculating similarities. Think of it like this. A higher perplexity value means I'm looking at a larger neighborhood around each point. A lower perplexity means I'm focusing on a smaller, more tightly knit group of points. It's a crucial setting because it changes the scale of the relationships the algorithm sees. I disagree with this statement. The optimal perplexity is not a one-size-fits-all solution. It varies greatly from dataset to dataset. You need to experiment to find the best value for your specific data. Think of it like Goldilocks and the Three Bears. You need to find the perplexity that's just right for your data. TSNE uses perplexity to find the best balance between local and global structure in your data. High perplexity values let you see the bigpicture, revealing broader patterns. Low perplexity, on the other hand, gives you a closeup view highlighting local clusters. I think this statement is correct. When you use higher perplexity, you're telling TSNE to consider a wider neighborhood for each point. This leads to a visualization that emphasizes the overall structure and large-scale relationships in your data. Yes, this is a key aspect. Perplexity doesn't specify the exact number of neighbors, but it directly dictates the range. It's like setting the radius of a circle around each data point. A larger perplexity means a larger radius, encompassing more neighbors in the similarity calculation. This is partially true. Lower perplexity will make clusters tighter. However, whether these clusters are always more distinct depends on the data itself. This question tests your understanding of how the perplexity parameter in TSNE affects the visualization of your data. I see perplexity as a control knob in TSNE. It adjusts how many neighboring data points are considered when figuring out how similar one point is to others. Think of it like this. A higher perplexity means I'm looking at a larger neighborhood, while a lower perplexity means I'm focusing on a smaller, more immediate group of neighbors. It's all about the scope of my local neighborhood. This directly relates to the perplexity parameter. A higher perplexity value tells TSNE to consider more neighbors when calculating similarities, creating a wider neighborhood. Conversely, a lower value focuses on a smaller, more tightly knit group of neighbors. I find it helpful to visualize this as the radius of a circle around each data point. Higher perplexity means a larger circle, encompassing more neighbors. This question gets to the heart of how perplexity shapes the TSNE output. We are looking for how changing the perplexity affects what we see in the visualization. The answer hinges on understanding that this parameter influences the local neighborhood size, thereby impacting the overall structure of the visualization. It's all about seeing the big picture, or the smaller details. This is the overarching theme. The entire exercise revolves around grasping how T-distributed stochastic neighbor embedding, TSNE, a dimensionality reduction technique, is impacted by the perplexity parameter. I'm focusing on how this parameter influences the resulting 2D visualization of the high-dimensional data. I see a larger neighborhood here. When you increase perplexity in TSNE, you're telling the algorithm to consider more neighbors for each data point when it calculates similarity. Think of it like expanding your social circle. You're considering more people when figuring out who's similar to whom. A smaller circle now. A lower perplexity means you're narrowing your focus. The algorithm only considers a few close neighbors for each data point. It's like focusing on your closest friends. You're only considering a select group to determine similarities. Let's zoom out. Higher perplexity lets TSNE see the big picture, revealing large-scale patterns and relationships between different groups of data points. Let's zoom in. Lower perplexity helps TSNE focus on the finer details, resulting in distinct, closely packed clusters of similar data points. This is the core question. We are investigating how the perplexity parameter, a key setting in the T-distributed stochastic neighbor embedding, TSNE, algorithm, affects the visualization of high-dimensional data after reducing it to 2 dimensions. The impact of perplexity on TSNE's outcome is the main focus of the analysis. We want to understand how adjusting this crucial parameter shapes the resulting visual representation of the data. Perplexity is a control setting in TSNE. It determines the size of the local neighborhood considered when the algorithm compares how similar data points are to one another. I like to think of this like a circle around each data point. Perplexity affects the radius of that circle, determining how many data points are considered neighbors. This question explores how the perplexity parameter affects the results of T-distributed stochastic neighbor embedding, TSNE, a technique I use to visualize high-dimensional data in 2 dimensions. I'm interested in seeing how changing this parameter changes the way the data is shown. This is the core question. I need to understand how adjusting the perplexity setting influences what I see in my TSNE plots. It's like adjusting the zoom level on a map. Different settings will reveal different levels of detail. This statement is correct. Perplexity doesn't set the exact number of neighbors, but it dictates the approximate range. A higher perplexity considers more neighbors when figuring out how similar data points are, while a lower perplexity focuses on fewer neighbors. Think of it like choosing how many people you consider close friends. A larger group means more friends. A smaller group means a tighter circle. This is also correct. Using a higher perplexity value means I look at a broader neighborhood, which helps me see larger scale patterns and relationships in the data. It's like looking at a map with a wide-angle lens versus a zoom lens. The wide-angle lens shows me the broader picture. While it often leads to tighter clusters, it's not always the case that they are more distinct. The level of distinction also depends on the data itself. It's not a guaranteed outcome. This is incorrect. The optimal perplexity depends entirely on the data set I'm working with. There is no single, best, value that works for everything. It's like choosing the best camera lens. The ideal one depends on what I'm trying to capture. I'll need to experiment with different values to find the best for my specific dataset. These are the different options provided to me as potential answers about perplexity's influence on TSNE visualizations.